and today's speaker is certainly not one of them. Michael Turner claims to have been born in Los Angeles sometime in the first half of the 20th century, but he adamantly refuses to release the long form of his birth certificate. He graduated from the West LA School for Wayward Youths in the class of 1967, along with his best friend Charles Manson and Turner's then girlfriend Squeaky Frog. As an undergraduate, he attended the California Institute of Technology on an athletic scholarship as a member of the Caltech's men's synchronized swimming team. After graduating Caltech, he enlisted in the United Federated Forces of the Siamese Liberation Army, eventually rising to the rank of Generalissimo. After military service, he attended Stanford University, and after a brief hiatus working with Al Gore inventing the internet, he received a PhD in physics working on gravitational waves under the supervision of Bob Wagner. Michael first came to the University of Chicago in 1978 as a Fermi McCormick postdoctoral fellow. One of the things Chicago does best is to recognize exceptional scholars with the potential to shape a discipline early in their career and then nurture, encourage, and promote them. Chicago immediately recognized that Turner had promised to have promise, and he rapidly rose through the faculty ranks as assistant professor, associate professor, full professor, and finally appointment to his present position as former Governor Bruce Rauner Extinguished Service Professor of Astronomy and Astrophysics and the college. Turner was instrumental in developing the Chicago School of Particle Cosmology, originally started by David N. Schramm. The Chicago School of Cosmology grew to encompass Fermilab, where Turner and an unnamed colleague started the world's first astrophysics group at a national accelerator laboratory. The now established field of particle cosmology was founded at Chicago, and we remain the world leader with the establishment of the Cobley Institute of Cosmological Physics, now directed by Turner. Turner's scholarship was recognized by many awards and recognition, including election to the National Academy of Sciences, the American Academy of Arts and Sciences, the American Philosophical Society, the International Brotherhood of Metaphysicians, and the Warrenville Center for Scientific Culture. In public and professional service, Turner served in the George W. Bush administration as Assistant Director of the National Science Foundation and head of the Mathematics and Physical Sciences Division. He also served a term as President of the American Physical Society before impeachment proceedings, and still prefers to be referred to as Mr. President. Since retiring from competitive synchronized swimming after a series of uncontrollable accidents in the pool, Turner has become an avid cyclist. Many days he can be found on the lakefront trail. Don't let the training wheels fool you, he goes fast. In today's colloquium, he will demonstrate that his counting skills are undiminished by age and tell us how many numbers it takes to determine our universe. Please hold your applause.
I'm glad that a close friend was introducing me and not an enemy. Well, I did not go to school with Charles Manson, but I did go to school with Jeff Bridges and Bonnie Raitt. And, okay. In the brief time remaining, I'll try to tell you about how many numbers it takes to determine the universe. So, over the past 30 years, we've seen revolutionary progress in our understanding of the origin and evolution of the universe. when I came to Chicago, a high redshift galaxy meant like a redshift of a 10. And everybody knew what Q naught was. And now, when we talk about Q, we're talking about quark soup and quantum fluctuations in the early universe. And this progress has allowed us to ask questions as deep and profound as this one. How many numbers does it take to determine our universe? And so I thought that was a fitting topic for the colloquium. Rocky mentioned the Chicago School of Cosmology. The University of Chicago is famous for changing the course of fields. And I think the Chicago School did just that by bringing together particle physics and cosmology, and that, I believe, resulted in this revolution. This is a slide that I don't know where it is. Probably many people don't know what a transparency is. And this was one of Dave Schramm's transparencies that was well used, and it had to be restored. We got a team that was previously working at the Vatican to restore it, and it's pretty good. I think the first meeting that brought cosmologists and particle physicists together and sold t-shirts was at Fermilab in 1984, and here's a t-shirt from that meeting. And here's one illustration of the evolution of the universe. Here we are today. Here's the very beginning. 30 or 40 years ago, cosmology ended at Big Bang nucleosynthesis. And that was it. And we couldn't talk about this earlier era because of the Hadron Wall. And I won't talk about what the Hadron Wall is, but some people will know that's when you had overlapping hadrons. But once it became clear that it was point-like quarks, that opened up the whole early universe. And so you have things like inflation and phase transitions and the production of dark matter. This coming together, one way to illustrate how influential it was, it literally changed the conversation in cosmology and the vocabulary from to words like dark matter, inflation, dark energy, WIMPs, baryogenesis, cold dark matter, quark soup. It also changed the players. So cosmology used to be done by a handful of astronomers, and now it's done by, I don't know, probably 1,000 or more particle physicists, nuclear physicists, astronomers, and various other people, and the experimental techniques. Okay, back to the question. This is such a great University of Chicago question, and I'm tempted just to stay on this slide for the rest of the time, because we could talk for an hour. What does this question mean? So a couple of coffees this last week, I talked to some of the fellows about, what does this mean, and how could it take zero numbers? But it's a great University of Chicago question, where what's most important is talking about the question rather than the answer. At some point you'll realize there isn't really an answer to this, but it allows you to think deeply about the universe. And of course, there are plenty of numbers to choose from in the era of precision cosmology. So I put about as many numbers as I thought you would tolerate. One of the most precise numbers that we know it to 0.15% is the temperature of the microwave background. The age of the universe we know to about 1%. The density parameter, omega naught, we know to 0.2%. The Hubble constant is so fun because we always know it very accurately. Sorry, very precisely. So we have two values, and we'll come back to that, the number of neutrino species. Anyway, there's a whole list of, perhaps the number we know most accurately is the sound horizon at decoupling, and I forget what percentage, it's probably 3%, or Selene could tell us how accurately. So we have a whole bunch of numbers to choose from. And what got me thinking about this, and probably get, if I ask people how many numbers does it take to describe the universe, you would say, oh yeah, I went to some Planck talk, and I think it's 6. And so Planck, the Planck collaboration's favorite fit, their standard fit to the cosmic microwave background has 6 numbers, and I'll talk about them in a second, but we should ooh and ah about their all-sky map. Not quite as high resolution and not as precise as the South Pole Telescope's map, but it covers the whole sky. And of course, what you really ooh and ah about is when you take the spherical harmonic multiple transform of this, and what pops out are these beautiful acoustic peaks, and then this is the Rorschach that determines whether you're a theorist or an experimentalist. If you're a theorist, you can see about 11. If you're an experimentalist, well, I used to joke, Bruce Winstein could only see 1. So if you're a hard-nosed experimentalist, you see fewer. But the 6 numbers are the 6 numbers that determine this theoretical curve that basically goes through all the points. Here are the residuals. So this is the temperature difference on the sky squared versus multipole number. And the 6 numbers are the baryon density, the matter density, the amplitude of density perturbations, the inhomogeneity in the universe, the spectral tilt of the density perturbations, how much they deviate from scale invariance, the sound horizon that I talked about, as shown in these acoustic oscillations, and then the optical depth to last scattering. So what fraction of the photons of the microwave photons from last scattering undergo a scattering before they get here? So those are the 6 numbers. But let me show you some other people's opinions. I mentioned, cosmology before the Chicago Revolution, and Alan Sandage wrote a very influential paper in February of 1970, and he talked about there's just 2 numbers in cosmology that we need to describe the universe. And so those 2 numbers, some people in the room will remember them, at least one of them. One of them is H naught and the other is Q naught. So here's the scale factor of the universe, and H naught is the slope of this, and Q naught is the second derivative, basically, of this. So it's the droopiness. So the slope gives you the age, and the droopiness, is it really decelerating a lot? It's called the deceleration parameter, so it's defined with a minus sign. Is the universe slowing down enough to recollapse? So H naught actually has been measured, and here is a history of the measurements of H naught, starting in Hubble's time, and even before Hubble's time, up around 600, falling down to the current value around 70, and of course our own Wendy Friedman has played a very important role in wrestling H naught into submission. And now Q naught, so this is a paper that I recommend to you. It does not get enough attention. And its main consequence has been the education of at least one astronomer. So it's not measurable. What do I mean by that? Well, there it is. You can't measure it both with accuracy, so accuracy and precision. And so the referee, the astronomer referee, I think that's the person we've most influenced, said, what do you mean by accuracy and precision? Aren't they the same thing? And the astronomer referee got very excited and said, astronomers don't know those terms, and you need to define them in the abstract. So there it is. You can go look on the web, you can go look on the archive, and the original paper did not have those 2 defined. So that's been our most influence, but it is interesting that you cannot measure Q naught. I don't want to dwell on it, but one of Sandage's numbers was not even measurable with accuracy and precision. So I thought I would go back a little earlier. Oh, you see that astronomer smiling. I thought I would go back a little earlier. There was a time when it looked like we just needed 1 number. So Johannes Kepler was obsessed with the Platonic solids. I think there are 5. How many? 5 of them, Rocky? And if you nest them in the right way, it gives you the spacings of the planets. And so that leaves one parameter. What sets the scale? So that's the astronomical unit. I'm not sure Kepler ever wrote a paper saying one number explains the universe. I asked Rocky, I don't think he did. Lord Rees of Ludlow, our good friend Martin, wrote a book saying it takes just 6 numbers to determine our universe. So notice the number 6 again, but this is going to illustrate the richness of the question because it's a different 6. I'm not even sure there's any overlap. So first of all, 3. You need 3 space-time dimensions. You need gravity to be weak. And I'm not sure what units he was using here, but very weak compared to electromagnetism, 10 to the minus 36 of electromagnetism. You need, well, he's British, so he had to work in 007. So another important number is that the energy release in cooking 4 hydrogen atoms to helium is 0.7%. A flat universe, small lambda, and he called the amplitude of the density perturbations Q, and it should be 10 to the minus 5. So that's the level of inhomogeneity revealed in the microwave background. So those are his 6 numbers. Now remember, we all know Martin, and Martin is really smart, and this is such a great picture of the intensity. And of course, he's a lord, and former president of the Royal Society. So one of his other colleagues, who's a famous British cosmologist, Michael Rowan Robinson, it took him 9. Which maybe you should view that as being good because, Martin is like God, and so he got it down to 6. So if you could get it down to 9, you're 2/3 of God. And his list looks, a lot of the same numbers here, the baryon density, cold dark matter, he throws in the hot dark matter, lambda we've seen in lists before, the microwave background, the age of the universe, so on and so forth, star formation history. Okay, so that's his list. Everyone puzzled about 0 numbers, so let me pause here and shift to 0 numbers. So Murray Gell-Mann, it's probably 20 years ago, in the early days of string theory, believed that there was only one self-consistent string theory, and that that had to be the theory of everything. And Murray used to famously say that all the rest of science was just environmental science. And so the idea here is that you have the physical theory, and that starts somehow the universe starts, and the rest is just determined, it's just weather. I think he actually used the word environmental science, but weather is the analogy that I'll pick up here. So that allows us to talk a little bit about Einstein. So Einstein famously asked, did God have a choice about the laws of physics? This is not actually the letter where he asked that. This is his letter that he wrote about a year before he died to the German philosopher Erich Gutkind, basically trashing religion. And but anyway, it doesn't matter. So Gell-Mann would say no, the creator did not have a choice. Rees, so actually let's go back to Martin here. So hidden in this book is the multiverse. And so basically Rees would say, well, we had a multiverse, and so he tried them all. So the creator tried them all. Okay. Another 0 numbers is the Hartle-Hawking no-boundary wave function of the universe. And so we live in a quantum mechanics governs physics, and so you should be able to write down a wave function of the universe that determines the initial state, and this wave function of the universe in their formulation of the problem is specified by the theory of everything. So what goes in the wave function of the universe is the Hamiltonian for the theory of everything. So again, 0 numbers, the rest is weather. Okay, so let's sum up right now. So where are we? So this is a great University of Chicago question, because you know, clearly the applicants in their essays were talking about different approaches to this question. Oops. Let's see, Ted, do we have another pointer? I'll keep talking, but yeah, my laser has run out here. So first of all, the idea that you have 0, maybe 1 or 2, is that there's an underlying physical theory, the laws of physics, thank you, and the rest, there we go, and the rest is just the evolution of the universe. The second, you know, trying to categorize these, the second one is really a descriptive, you know, we're just going to describe the universe. And so maybe the simplest to see is sandage. So the universe is expanding. The two basic things are how fast is it expanding, that tells you the age. And the other one is how much is it slowing down? Well, it isn't slowing down, but nonetheless, that would tell you its destiny. And, oh, I've thrown Kepler in here and Rowan Robinson, and I'm going to throw Planck in here for now. And so these descriptive are largely theory agnostic. We don't need the theorists. We're just going to measure a bunch of stuff and write it down. And then finally, the anthropic view, that the way we got this universe is that there are laws of physics that have the properties that lead to our existence. So it's kind of going in a very different direction. It's actually a fun intellectual exercise. Oh, I said the A word. I didn't mean to say the A word. So 3 different approaches. Let me come back to Planck, because Planck started all of this, and I maybe have not been completely fair to Planck in the way I characterized, dare I hold 2 of these. So while Planck really was descriptive, its numbers are motivated by the lambda CDM framework. So a cosmological constant plus cold dark matter. And just to review that, so this framework, the reason the universe is accelerating is a cosmological constant. So quantum vacuum energy is the dark energy. This model, the reason that we have a flat universe and a universe that has inhomogeneity that's nearly scale invariant is there was an early burst of tremendous expansion, inflation, that explains all of this. And then finally, the dark matter that holds together galaxies is slowly moving particles that are left over from the earliest moments of the universe. So underlying that, let's see, this is the one I have to press. So the Planck approach is not purely descriptive, because it somehow secretly knows about this theory. So I want to build upon Planck, and here is the startled George Estathiou, because I think we should be able to do much better than what Planck did. It was a little too agnostic. It did not set high enough goals. So what's embodied in lambda CDM and what we've learned from the microwave background is stunning, but let's review the 6 numbers. So 4 of them are purely descriptive. The matter density, the baryon density, the age of the universe, the optical depth. It's just like, you know, it's what Al Gore wanted. And Al Gore and I would have these dialogues, and he said, we need to send everyone out to measure things about the universe, and then we need a way where they compile them somewhere, and we'll form a big book, and that's science. But science is more than that. Science is understanding, and so just describing things is not enough. Now, two of the parameters, the amplitude of the density perturbations and the spectral index of them, or the tilt, do start getting at a more fundamental understanding, at a more scientific rather than descriptive approach. Okay, so what was the question? Again, this is the University of Chicago, so we have to keep returning to, did I understand the question? So let me see if we can, so how many numbers does it take to determine our universe? So let me try to parse that. So the middle part of it, I think, is a verb. No, that's a verb too. Anyway, there are two pieces I can parse. So how many numbers? So we're looking, well, this is the University of Chicago. I was going to say for a real integer, but maybe it's going to be a Euclidean approach, so it could be imaginary, but we're going to keep it simple. So positive integer, and it can't be imaginary. Okay, and what are we looking for down here? So we're not looking for what Laplace wanted. So you remember old Simon Pierre? I remember him. He was one of my students, not one of my best students, but he was a pretty good student. And talked about, if I knew the position and velocity of every particle, I could predict where they would be in the future. So clearly, that's not what we're talking about when we determine our universe. What we are talking about are the most important features and the statistical properties. I think that's sufficiently vague for the University of Chicago. So the most prominent features of the universe and its statistical properties, not the position of every particle. Okay, so that's the question. Now here's the answer, and I don't think I have a good name for this yet. I was looking for something really catchy. Either automatic or the self-booting universe. So this is the goal of 0 parameters. And the idea is that the laws of physics, not initial conditions or parameters that you just put in, determine the present large-scale features of the universe and the statistical properties. So going back to this analogy with weather and climate, so the statistical properties, that's the climate, not the weather. We're not going to predict the individual, what kind of galaxy we're in. And this approach, at least the way I'm advocating it, is agnostic to this question that Einstein asked, whether or not the theory describing the universe is unique. It's agnostic to the watchmaker. A really good question is, and this one's too hard for me, is why is there something rather than nothing? And who started our universe? So I'm agnostic. I'm not interested in that. And because that could be God, that could be freshman physics lab in an advanced civilization, and this was a seed project. And finally, it's also agnostic to the existence of a multiverse, or again, I'm trying to coin some new words here that are less ugly, the ensembleverse. So it could actually be that, there are different pieces of the universe and there's a statistical ensemble, and that some advanced civilization will have to talk about that statistical ensemble. But this automatic approach is agnostic to that. That's for someone else to worry about. The main assumption is that there are laws of physics, and the key idea is that the universe got this way not because of initial conditions, but self-booting, it had to turn out that way. So let me give you the biggest success of this approach, because I think it'll help you understand this. So the primordial mix of elements in the most pristine samples of the universe have about 75% hydrogen, 25% helium, a few parts in 10 to the 5 deuterium, and a few parts in 10 to the 5 helium-3, oh yeah, and then there's some lithium-7, a few parts in 10 to the 10. So you could just say, well, that's the way the universe started. That's what they had in that freshman physics lab. That was what was on the shelf. We know that, I mean, I'm telling you this and you're saying you're crazy, because we know the explanation is that it's automatic. We don't need to specify that. If you take the known laws of nuclear physics, the expansion history of the universe, that determines the mix that we have today. And so, wrong one. Oh, let's see, that's not the picture I wanted. Okay. Because I'm selling t-shirts. You're going to see a lot of t-shirts today. Okay, so we all know that's success. So that's the basic idea. What I would give as partial success, and remember this is the University of Chicago, so it's, you know, we don't give easy grades here. So partial success, you should go home and brag about that. So baryogenesis. So in more recent times, a big debate had to do with how come there's no antimatter. And in fact, the debate was a bit confused because other people, including Zeldovich, said, well, the real number to explain is all the photons for every baryon, the high entropy of the universe. And nowadays, the question is really rephrased as a small baryon asymmetry. A small asymmetry between the number of baryons and antibaryons compared to the number of photons, so an asymmetry of about a part in 10 to the 10. And then as the universe cools and all the antimatter annihilates, you're left with about 6 baryons per every, let's see, you're left for 6 baryons for every 10 to the 10 photons. Okay, so where did that come from? So the idea of baryogenesis is it's automatic. This large-scale feature of the universe happens because of baryon number violation, CNCP violation, and the expansion of the universe. That determines that number. It's automatic. You do not have to put it in. It's not an initial condition. So that's the idea. And let's see, that idea, this is a t-shirt Rocky and I designed in 1981, so this is an early production of the, there it is. So it's baryon number violation plus the expansion of the universe gives you matter. So another example that's, now of course we don't know all the details, or if we know them, Carlos Wagner is not telling us them yet. Structure formation. So this again is a partial success in the sense that if we now specify the initial inhomogeneity, okay, hopefully we'll do better than that. Hopefully it will come from inflation. That and gravity and the expansion of the universe and the laws of hydrodynamics determine the outcome. So maybe that was a cheap success, but this is the idea, is that the present state of the universe is that way because of the laws of physics. There's no numbers that have to go in to cook this. Okay. Oh, yeah. So I'm going to tell you in a second that we don't know the theory of everything, so this could take a while. But I'll just, the one big success, let's see, started in 1948, and we're, you know, yeah, more than 70 years later. So sometimes these take a while. So some of you may know this is a paper by George Gamow and his collaborators that's called Alpha Beta Gamma. Let's see, Alpha is his student Ralph Alpher, Beta is Hans Beta, and then Gamow is George Gamow. And probably some of you have heard the story that Beta actually didn't do anything on the paper, but Gamow thought it would be cute if they had a paper, Alpha, Beta, Gamma. And by the way, having Beta on your paper is not a bad thing. I recommend it to all the students in the room. And the idea was the periodic table is made in the Big Bang. So a raging question in the 40s is, where do the chemical elements come from? Can't we find an automatic answer for them? And what's great about this paper is not very many correct equations in it. In fact, it really was describing the R process and not Big Bang nucleosynthesis. But it was a game-changing idea, and among other things, it predicted the microwave background. There's a paper that's less well known in 1964 by Fred Hoyle and Roger Taylor that pointed out that there was evidence for a large primordial abundance of helium, and that if you did this right, you could actually explain the helium. And then the discovery of the microwave background, and the rediscovery of the Gamow paper at Princeton, and Wagner, Fowler, and Hoyle wrote the first correct nuclear physics calculation of these elements, and it actually works. And Dave Schramm, Jim Gunn, and Gary Steigman pointed out that actually this might be a nice test bed for exploring the conditions in the early universe. We'll come back to that. The helium abundance, well, it got better over the years, but it goes back to 1964. The deuterium, that first measurement was made in 1998, and then, as I'll show you, that pins down the baryon density and then the microwave background. So some people think the microwave background is how we know the baryon density. It's a mere confirmation of what Big Bang nucleosynthesis tells us. And then we'll come back to probing the early universe with that. So here are the elements. The elemental abundances depend upon the baryon density, and helium is a linear scale, so a lot of helium gets made. Deuterium is a log scale, not much deuterium is left over, so if you can measure it, that gives you the baryon density, and then helium-3 is complicated and lithium's more complicated. Just focus on these two. And so the measurement of deuterium pinned down the baryon density, and so here is the measurement of deuterium. Here's omega baryon H squared. This is the Big Bang prediction, and then here's what the CMB confirmed. And then the abundance of the amount of helium produced depends upon the expansion rate of the universe way back when the universe was seconds old and these processes took place. And the Chicago School parameterized that in terms of number of neutrino species, and the more light species you have, the more helium you make. And so by measuring the helium today, you're really measuring the expansion rate in the universe early on. Okay. We don't have the theory of everything, so how can you possibly make this paradigm work? Well, okay, so that makes it a little bit harder, but this is the University of Chicago. We do the hard problems. So we may, in the absence of a theory of everything, need some descriptive parameters that can help us discover the theory of everything, confirm some of our best ideas, or tell us that some of our ideas are just completely wrong. And so in the absence of a theory of everything where you can just write down all the equations and make the predictions, we're going to try to connect descriptive parameters with the underlying physical theory. And again, we don't want to give up along the way and take the easy British route of being seduced by the multiverse and saying, oh, we can understand all these numbers just because if they weren't that way, we wouldn't. So that's like being seduced of the sirens of the multiverse. So let me give you one example, which is a trivial example, but I wanted to put it in so that there would be a part of the talk that Rocky would understand. And how can you learn from a descriptive parameter? If you measure something really precisely, you can learn from it. So one of the numbers that we measured most precisely is the microwave background temperature. Another number is the age of the universe. So the microwave background, less than 1%, the age of the universe, about 1%. In the context of this automatic universe, they're not that interesting. They just specify the current epoch. They just tell us where we are today. They don't tell us anything fundamental. But the Wendy-Friedman equation, oh, it's a different, is it?
No relation.
No relation, okay. The Friedman equation relates the two. So relates the age of the universe and the density of the universe. So let's suppose, and this is the silly part, but I just want to show you how this works. Let's suppose that we thought the microwave background was all the energy density in the universe today, or the dominant bit of it. Then here's the Friedman equation. The expansion rate of the universe squared is 8 pi g rho over 3. The h naught is related to the age of the universe by a factor of 1/2. Here is the microwave background energy density, and you can solve for the age of the universe, and you get 984.1. Probably I'd get another significant figure, gigayears. Oh, we have another measurement that's 13.8, and those two numbers aren't consistent, and so that tells you there's more here than meets the eye. Now, I know this is a really trivial example, but there's a more burning example here. This is a more general principle that by measuring these descriptive parameters to high accuracy, 2 different ways, you can learn something. So we've measured h naught. Once again, it always seems that the measurements of h naught come in pairs. So when I first arrived here, it was 50 and 100. Now it's 67 and 73. And the 67, many of you will know, comes from the microwave background. And the 73 comes from the good old direct measurements using the distance scale and actually measuring the expansion rate of the universe. And there's a more than 3 sigma discrepancy. This is a plot of this discrepancy versus time. So the red are the microwave background measurements, and the blue are the direct measurements. And you can see that there's a big gap, and the gap has been, looks statistically significant. And so you might say, well, okay, somebody's right and somebody's wrong. But if you go back to this example, so we have 2 high precision numbers that disagree, and the problem was the assumption. The assumption here was that the universe was all radiation. So it could be that these 2 numbers are both correct, and they're telling us that something is missing. And the microwave background is, I mentioned this earlier, Planck assumes lambda CDM. So maybe lambda CDM is not the whole story. And so there's going to be a way possibly to break the tie, or to well, this wouldn't necessarily break the tie, but having ways of finding out if one of these methods has an error that hasn't been discovered. Brings in Daniel Holtz and gravitational waves. His passion is to use gravitational waves to directly measure the Hubble constant. And you've heard about this before. The binary neutron star in spiral already has not settled it, but weighed in on this problem. And in fact, we had a very exciting workshop here in October. And we brought the microwave background people, and we brought people who directly measure h naught. And so at the end of the day, so this was a summary talk that Josh Freeman gave, and basically the group said the answer is new physics. They kicked each other's tires and said, I can't find out what's wrong with your method. It must be this assumption. Okay, so descriptive parameters can be important along the way. Okay, so everybody knows that we live in the era of precision cosmology. Okay, it may not be as precise as you think, and there could be some improvement there. And so we have some narrow gates where we know a lot about the universe. So let me start with the microwave background. So it's exquisite, it's simple, but we're really probing the universe over a fairly narrow redshift range, and these acoustic oscillations pin down a bunch of parameters that determine those acoustic oscillations to sub-percent level. But they leave much of the rest of the history of the universe untouched. Big Bang nucleosynthesis is very similar. It's another gate that any theory has to go through. So it probes this range of redshift of 10 to the 8 to 10 to the 10 very, very precisely. Pins down the expansion rate then to percent level and thereby the number of relativistic species to a similar level. So any other gates coming soon? Well, structure formation is a potential gate in the era of DES and LSST, where we can use gravitational lensing to study the growth of structure. We might be able to pin down the growth of structure and turn it into another precision gate. The expansion history of the universe using supernovae, that's already done a really good job, maybe getting better. 21 centimeter. The claim is that the 21 centimeter is even better than the microwave background. Whether or not we're going to be able to measure 21 centimeter well enough to get all those extra modes of the universe and create another precision gate remains to be seen. So I want to encourage, new ideas are necessary here. Okay, let me go on and talk about some opportunities on the horizon. So I've alluded to this a couple of times. So in thinking about the theory of everything, one way to get at it is, what are the degrees of freedom? What are the fundamental degrees of freedom? What are the particle species? Maybe some of them can't be produced at an accelerator. And cosmology can get at the ones that are light, that would have been present in the thermal bath and are relativistic at the time of Big Bang nucleosynthesis. So those are particles less massive than 1 MeV. And the microwave background, particles less massive than about an EV. And so precision measurements in both cases should be able to measure that number of neutrino species. Oh, that's right. So it's parameterized as the effective number of neutrino species. We really think there's only 3 neutrino species. But historically, we didn't know that. And this is another Chicago School convention. And so these are two important measurements. Inflation. So inflation could have occupied the entire time. I'm not going to spend enough time on it. It is an essential part of the automatic universe. Because another burning question in cosmology 30 or 40 years ago is, why is the universe so smooth with small density perturbations? And why is it so nearly flat? And must be initial conditions, but generic initial conditions wouldn't lead to that. So inflation really is a key part of this idea of a universe that automatically requires no parameters, no initial conditions. It just winds up the way it does today. And so it dramatically reduces the sensitivity to the initial state. And so here we can just build upon what Planck has done. So Planck has these descriptive parameters, so the amplitude of the density perturbations, the tilt, in their extended set, they have the variation of the spectral index. R, you've heard about in all of the gravitational, all of the CMB talks, it's the ratio of the gravity waves produced by inflation to the density perturbations. And so the one improvement that Planck needs is, let's relate those to what's causing inflation. And our best guess is that it's a single scalar field. That's our working model. And so all of these parameters can be related to that, and possibly, and thereby give us insight. I'm going to skip this. Well, I'll go back to this. So here's what we could learn about inflation from gravity waves. So if you have a lot of gravity waves, then you instantly learn that the scale of inflation involves Planck scale physics. If you don't have much gravity waves, it involves sub-Planck scale physics. So that would be a good hint about the theory of everything. So that's why people are so interested in detecting the gravity waves made from inflation, and the microwave background is probably the best way to do it. Let's see, I'm now on to starting to finish up here. And so I'm in the advice section. And so I'm going to give advice from me, which is what you'll listen to, and then from Steve Weinberg. So you can just sleep through Steve Weinberg's advice. Actually, the number of effective neutrino species isn't, if there were no new physics, it wouldn't be 3. It would be 3.045. You might say, why is that? Well, there's an assumption in the standard model that's not quite true. It's that when the electrons and positrons annihilate, neutrinos have already decoupled and are not heated up. And so back in 1992, Scott Doles and I had nothing better to do. The idea that you could actually measure this 1% effect was completely, there was no way that you could ever measure this. The microwave background anisotropy hadn't been detected. Now, so nonetheless, we said there should be an effect. This would be a good test of cosmology. And this likely is measurable by the stage 4 CMB experiments, that you could see the difference between 3 and 3.05. Okay, so actually today I was reading my email from the American Physical Society, and Steve Weinberg now has an advice column. And this is his advice to the next generation of model builders, and I thought, I'm giving a talk on that today, on the theory of everything. So what does Steve have to, he built a pretty successful model. The Weinberg model, the Weinberg-Salon model. So question from the APS, do you have any advice to offer the next generation? So he's very well read. And so I don't even know who Winston Churchill is, but apparently he's so important. Winston Churchill had a motto at the beginning of World War II, keep buggering on. In that spirit, I think it's better to do something than to do nothing. My advice is to try crazy ideas and innovative experiments. Something will come up. So yeah, that's probably pretty good advice. That's probably where we are, particularly on dark matter. Okay, so I've just given you a story where the right answer is 0. And I don't know how many people came up to me and said, how could the answer be 0? And now I've convinced you not only that it's possible, but it's the right answer. And so what is it? I forget who used to say, what could possibly go wrong with this program? What could possibly go wrong? So the initial conditions might matter. Oh, can you give me an example? Well, my favorite dark matter particle is the axion. And I really love inflation. And if you have inflation in the axion, then the axion density today depends upon the initial misalignment of the axion field, which is a random variable. Somebody rolled the dice, and we don't get to know. It's not averaged over the universe. It's averaged over the multiverse, and we don't have any information about that. And so this initial condition might matter. And there are other really smart people thinking about this, and Roger Penrose thinks we're thinking about the problem in all the wrong way. That when you think about the universe, it's all about the initial singularity, and I'm going to paraphrase him very poorly, but only some kinds of initial singularities are allowed. And then finally, I don't know if cosmologists are, part of the reason cosmologists and particle physicists got along is because they both have really big egos. And you really have to be fairly arrogant to think that you can understand the universe. But nonetheless, there may be some limits in cosmology. Historically, the universe has been often just beyond the reach of our biggest ideas and most powerful instruments. And so let me just mention a couple of small things. So since I was a graduate student, George Ellis has been writing about the fact that we're only privy to our past light cone, and that's a very small part of the universe, and we're generalizing upon that. The iron curtains. So my advisor, Bob Wagner, wrote a book, I actually forget the title, but it was something like The Last Horizon. So if you only can look at the universe with photons, the microwave background is 380,000 years, and you can't see any further back. If you had a neutrino detector, it's 1 second. Worse than that, and you say, oh, we're cleverer than that. We've got the elements that were made in the Big Bang. We have the dark matter that was made when the universe was 10 to the minus 10 seconds old. However, inflation is really interesting because its whole purpose is to be a curtain. It's to shield you from the initial conditions. And so maybe that's a problem with this program. How do you test things in a historical science? What is the level of proof? Let me illustrate the problem with Big Bang nucleosynthesis. So I think everybody, in science we never use the word believe, but I'm going to use the word believe. We all believe in Big Bang nucleosynthesis. Why? Well, because we didn't invent the particles, we didn't invent nuclear physics. We had nuclear physics, we had general relativity, we put them together. There were things that we measured. Let's see if I have another example. What about with dark matter? So dark matter is one where I like to use this term, closing the circle. We can close a circle with dark matter. So we know it's necessary to form structure in the universe. We think it's a particle. Well, that's definitely not proof. How could we prove it? Well, the one way I think we could prove it is a triple signature. We produce the dark matter particle at the LHC. We detect dark matter particles in our own halo, 1 Calar or Tau Privatera or Luca, and we see them annihilate. We see their signature in the annihilation. And then we start measuring, oh, let's see, their annihilations in the halo, say their cross-section is this, and to get the right number in the early universe, the cross-section has to be that, and then we learn about the cross-section from, so you can close the circle. It's like the same, it's like when you read letters of recommendation and all the letters are about the same person. So all the experiments end up telling you about the same particle. But this in a historical science is very difficult. Then there's hard and soft technology. So hard technology is maybe we're just not smart enough to build the instrument, or maybe it's too expensive. And then there is the soft technology. So in my spare time, I study neuroscience. And it turns out dogs cannot understand quantum mechanics. That's why Rocky's been trying to teach Rosie quantum mechanics, and it just doesn't work. And that's because their prefrontal lobe is not big enough. So is our prefrontal lobe big enough to understand the universe? I don't even know what that question means, because I know a dog doesn't sit there saying, oh my God, I can't understand quantum mechanics. Not even poodles complain about not being able to understand quantum mechanics. And then, oh, this one, I had to throw something in here about the nature of science, and done. So we can only disprove theories. This comes back to, how do you actually prove something? So we can't prove theories. And then this one just gives me a headache, and I don't think you should think about this. So when you teach about science, there is an assumption that there's an objective reality. And actually, the current days are testing that. What if actually, well, I have proof against this. I was going to say, what if all of you are just imagined by me? But then I would have a Nobel Prize. And so that's a proof that yeah, because I would have awarded myself a Nobel Prize. Okay, what did I, let's see. We did that, the limits. But hopefully this is not limited by our passion to understand the universe. So I think the correct answer is 0. I think it's a real University of Chicago problem, and I hope you enjoyed this. Thank you.
Thank you, Michael. We have time for a few questions.
So how do you close the circle on inflation?
Oh, so that's a really good one. And the short answer is I don't know. You might say, one might be tempted to say by detecting the gravity waves. And, if I were in a debate with someone about that, I would say, well, the person who predicted those gravity waves was Grischuk. And he predicted them before inflation was even here. You get those gravity waves as long as the early universe went through an exponential phase. And so, if you, in analogy to dark matter, you'd want to be able to produce the inflaton particle. And of course, the inflaton particle, it's like really challenging. So not only do we think it's really massive, well, maybe it's the Higgs. I don't think it's the Higgs, but maybe it's the Higgs. Not only is it really massive, but it interacts very weakly. So it's a double whammy. So I think inflation is going to be a very, very hard thing to close the circle with. I would die a happy man if we close the circle on the dark matter. If we could, I forgot the joke about that.
That's motivation for these girls.
That's my job, is to motivate.
Thank you, Leon. Other questions?
So let's say you find the answer to this question, how many numbers does it take to determine our universe, and it's a number that's not 0 or 1, so like some positive integer.
Let's suppose we find what?
The number, the answer, like some positive integer of how many
Oh,
numbers
right, it's 0.
determines the
Yeah.
universe. Yeah, and say it's not 0 or 1, there's some sense that the next question is, there's a physical reason for why it's 6, for example.
Oh, well, you know, this is, I'm going to give you a very slippery answer on this. So the number one thing in science is asking questions. And the footnote that goes with that is you will never ask the right question the first time. You always ask the wrong question. But by asking the question and parsing through it and discussing it, you come to a better question. And so, you know, we now know enough to ask this question, and to be provocative, there's sort of two limiting cases here. One is that it's all determined by the physical laws, and so we just have to wait till the particle theorists get the toe. And the other answer is it's the multiverse. So we're just going to have to measure a whole bunch of stuff, and I didn't want to talk about the multiverse, but the multiverse is exactly the headache you're talking about, because you know, Martin listed a bunch of numbers there, and how do you know those numbers aren't correlated? You know, how do you know that you've listed the right independent numbers, that you can vary those? That's the problem with the multiverse. Every time somebody tries to prove or disprove the multiverse, it says, well, if we varied this number, you know, we wouldn't get our universe. Well, how do you know you can vary that one independent of this one? And so the multiverse is a headache, but I don't even know if this is the right question, but I think we're in a strong position to argue for the automatic universe, that we don't need to worry about initial conditions.
So you talk about you know, the self-moving universe versus something like a fine-tuned universe, which has a few numbers that we can only measure. My question is, so if the theory is supposed to tell us something about statistical properties of the universe, which we're only aware of one universe at this time, is distinguishing between a fine-tuned and a self-moving universe even a scientific question?
Let's see, I may have not been so clear about what I meant about the difference between the statistical properties and large-scale properties. So the statistical properties would be like the distribution of galaxies. So what is specified if we buy this inflation version is the variance of the density in a homogeneity field. So that's a real number that's specified. And so we don't need, and that they're Gaussian, so we don't need multiple universes to verify that. And so I think I more or less dodged your question, but it's going to be difficult. You know, how can you falsify this idea of the automatic universe? Nobody asked that, but I think the answer is, I don't know.
Okay, let's take a final question.
This one I think is really concrete. In your example about the radiation-dominated universe, you related the age of the universe and the temperature of the CMB, and the factor that was involved there was big G, the gravitational constant. So why is it okay to have an extra number in that relationship?
Oh, well, we're given the laws of physics, and so we're given general relativity. So that's part of the toe. So that part of it.
Value?
Sorry?
Numerical value?
Well, we're given general relativity, maybe we don't understand the numerical value. I mean, so now you're asking, are there different versions of general relativity with different strength of, so I'm going to defer to the particle physicists on that and say that it is their job, maybe probably with our help, to get the toe. And yeah, I'm not going to count that as a parameter. I'm going to say we have a theory of everything. I'm going to be a little Gell-Mannian here.
Okay, there will be no KICP reception after this talk. There will be speaker harassment for people without PhDs to come forward and stump the chump. And those of us who have PhDs are excused, but before we do that, let's turn it for a really big